So I'm Nicolas. I'm a PhD student here in Antwerp. And before I became a PhD student, I studied for half a year in Germany, and there I got to know this field of mathematics called model theory. Oh, I wanted to set a timer actually to keep track of time. I noticed that many things which you would like to be able to study in algebra, and many questions you want to answer, suddenly become much more elegant, and many proofs become much easier once you translate a question, which might be purely algebraic, into this framework of model theory. And that's what I want to talk about today. So what I don't want to do is give a definition of what is model theory and what do model theorists do. Instead, I just want to give you the framework and relate this framework to objects from algebra, which you know, and give you then this big theorem from model theory in this framework. And then, so I guess this is the table of contents. So that's the first part of the talk will be, and the biggest part of the talk will be giving you this framework of model theory. What kind of questions can one ask within this framework? That will be the second part. And then the final 2 slides of the talk will be one application, which is a theorem just from algebra or from algebraic geometry, if you want, which can be proved, I think, elegantly using these model-theoretic techniques, which I think should be in every algebraist's toolbox. So that's the plan. OK, so the framework I want to talk about is a general framework which, in a way, a bit like category theory, lets you encompasses many algebraic objects which you know. It's a bit less ambitious than category theory. It works especially well for objects which can be described by quote-unquote constants, operations, and relations. Let me give some examples before I make this precise. So for example, a ring is a set with some operations, 3 binary operations, plus, minus, times, which go from a squared to a, and 2 distinguished elements, which I call constants, 0 and 1. And a partially ordered set, for example, is a set endowed with a binary relation. Binary relation means a subset of a squared. And you can also combine relations and operations. An ordered group, for example, you would define as a set plus some binary operations, plus and minus, a fixed constant element, and some binary relation. OK, now, each time I write between brackets plus some conditions, of course, a ring is not just any set with any 3 functions from a squared to a and any 2 distinguished elements. You have to put some conditions. You want operations to be associative and this and that. Let's worry about these conditions later and just now focus on the fact that the data which specifies this structure uniquely it's a set plus some operations plus some relations plus maybe some distinguished constants. And the fourth and final example are vector spaces, so over the field of real numbers, also fit in this framework, which I haven't really formally said yet. An R vector space is a set plus binary operations, addition, subtraction, a constant 0, and for each real number, a unary operation. So by unary, I mean just from A to A, which corresponds to multiplication by R, which is maybe a bit different from how you would normally see a vector space as having addition, subtraction, and some map from R cross A to A. But this doesn't translate neatly in this framework, which I'm about to present. So you really need maps which are defined on A or on powers of A. Good, so let me now make precise what I mean. So I will say this very precisely and pedantically first, and then a bit less formally. So very precisely, what you need is you need to specify, OK, what is the data which I want to give to my objects? So very formally, I need a set K of all the constant symbols which I want to have. And for each natural number n, I need to have a set In of all the n-ary function symbols, and a set Jn of all the n-ary relation symbols. So let me immediately jump to examples, because this is very abstract. So for example, if I want to talk about rings, then I will specify what signature I use. The signature I use will be consist of, OK, I want 2 constant elements, 0 and 1. So my set K will consist of two elements, 0 and 1. This is to say, whenever I want to specify a ring, I have to specify two special elements, 0 and a 1. And I have to specify three operations, plus, minus, and times. So my set I2 of the binary operations symbols consists of three elements, plus, minus, and times. And all the other INs and JNs are empty. And similarly for the R vector spaces, I said I have one constant 0, two binary functions, plus and minus, and one unary function for every real number. So I just set my I1 equal to R. And all the other IN and JN are empty. So completely formally, I have to say what are my constants, what are my binary functions, my ternary function, and so on, what are my binary relations, my unary relations, and so on. In practice, usually model theorists will be a bit less pedantic and will usually assume that it's clear that if I write plus, I'm not going to use this for a ternary relation. I'm not going to use it as a constant symbol. So usually, if model theorists will write the signature of ordered groups, for example, and just say, OK, I want to work with a signature with plus, minus, 0, less than or equal to, and assume that the reader knows that less than or equal to is not a quaternary operation or something, but a binary, that we are going to use it only for binary relations. So,
do you have an example where not all the JN are empty?
Yeah, just the one over here. So I guess if I work with a binary, if I have a binary relation, then this JN, J2 will contain the binary relation symbol. Yeah. So here the K would be just 0, I2 will be plus and minus, and J2 will be the less than or equal sign. So this is not completely formally correct, but just pointing out that most of the time this is how we will do it. OK. And then when you have such a signature, then you can say that some object is a structure in the signature. And this is exactly what you expect it to be. So I want a structure in the signature is a set A. And for every constant symbol, I specify a specific element in my set A. So for every symbol C in K, I have to fix an actual element, an honest element, C, I write superscript A in A. And for every n-ary function symbol, F, I have to fix an actual n-ary function from A to the n to A. And for every relation symbol R in Jn, I have to fix an actual relation, n-ary relation on A. And in this way, if I have a ring, for example, an actual ring, then I can naturally see it as a structure in the signature of rings by, associating to the plus symbol the addition operation, and to the times symbol the multiplication operation, and to the 0 the neutral element of addition, and so on. And the same for R vector spaces can naturally be seen as a structure in this language of R vector spaces. Sorry, I said this. I wrote this before, so I was hoping to say signature all the time, but I also say language. I mean them as synonymous. So,
I was wondering, why do we make a difference between functions and these relations somehow, as we can also consider functions as relations? Strictly, functions can also be a subset of. The map FA, for example,
right.
is just a subset of AN plus 1 with some specific conditions.
Yes, so the question from London, I'm repeating, I guess, for the online audience. So the question is whether we cannot just restrict ourselves to relation symbols, since a function can be described as a relation in one extra variable in a way. It's true, yeah, and I guess I could also allow function symbols which have 0 inputs and then not work with constant symbols either. There is some arbitrariness in the choice here, and I will come back to this. OK, and then one can define in the obvious way what is a morphism between, for one fixed signature, one can define in the obvious way what is a morphism between them, and a substructure, and an embedding, and an isomorphism, and so on. So let's go for example, over the notion of homomorphism of structures. So you have one signature L, two structures A and B, and you have, for example, some binary function symbol, like think of the symbol plus or something. Then if A and B are both structures in this signature, it means that to both A and we have on A an honest binary operation, so a map from A squared to A, on B an honest binary operation, so a map from B squared to B. And to say that H is an homomorphism means, among other things, that it should make the map on A correspond to the map on B. So H of x plus y should be H of x plus H of B, informally speaking. And an isomorphism is a homomorphism of which the inverse is a homomorphism, and a substructure is a subset which is closed under all the functions. So yeah, all the things which you would expect them to be. So in this sense, L structures form a category naturally. Okay, and you can talk about L structures to be finitely generated and finitely presented and so on, but this is not going to play any role in this presentation. Good, so just to say, this framework captures these these notions which you know from ring theory, group theory, and so on. Before I continue, two little caveats. So I said that, for example, a ring can naturally be seen as a structure in the signature of rings by interpreting the addition symbol as the addition operation and so on. But I want to point out that at this point, I didn't say anything about what conditions I put on all these functions. So even though every ring can be seen as a structure in the signature of rings, the converse is not true. So a structure in the signature of rings is just any set with a priori any three binary operations which I put on that, not assuming associative or commutative or whatever, and any two distinguished elements, 0 and 1, which may coincide maybe, and I don't assume anything on them. So at this moment, there's no conditions on these functions, on these relations and elements whatsoever. This will come. And the second thing, and this is also coming back to Lander's question, I think, is why did I choose for the signature of rings 3 binary operations and 2 constant symbols? You might think, oh, I would define a ring as just having 2 binary operations and everything else follows from them. So the 0 element is uniquely determined by as the neutral element of addition, the 1 element is uniquely determined as the neutral element of multiplication, and subtraction is just undoing addition. So why do I have to specify these 3 function symbols and 2, or why did I choose this? Why not choose plus, just only plus and times, or plus times and 0? Or if we can specify many things, why not be even more redundant and also add a symbol for a unary function for taking the square of an element? So on the one hand, the choice is arbitrary. So yes, you are right. There is no canonical choice, and one could have made other choices. And that is also part of the power of model theory, that you can make a choice which is appropriate for the kind of problem you want to solve. But I can say a bit more, is that as a general rule of thumb, a good choice is one which is minimal, but such that the induced notions of homomorphism and substructure and so on correspond to what you naturally expect that they should be. And so I said that in the signature of rings, as I give it, the homomorphisms correspond to the ring. If you take them between rings, then the ring homomorphism between the two objects correspond to the homomorphisms in this structure. And substructures are subrings and so on. But if one would take the thing on the right with just plus and times, then a substructure need not be closed under subtraction and need not even be non-empty, need not contain the 0 element or the 1 element. A homomorphism need not send 1 to 1 and so on. So that's why, so from these smaller ones, they don't give you the right notion of homomorphism, which you would expect, don't give you the right notion of substructure, whereas the bigger one is more objectively redundant. Yes. Okay. Any questions so far with the structures and signatures? Good. So what else can we do with them? So once you have a signature, you can make somehow a formal computation in this signature. So think of the language of rings immediately, the signature of rings. You could write down, you could take variables, x1, x2, x3, and write down something like x1 plus 1 times x2 minus x3. So this is not, I'm not writing some computation down in a specific ring. I'm just writing down an abstract, yeah, polynomial, you could think of it maybe, but careful. And this is something I can do generally. So if I have a a signature, I can use variable symbols and the function symbols which I have, and the constant symbols which I have, to write down such a formal computation. It's called a term, L term, if L is the name of the signature. So you can think of it a bit like a polynomial in the language of rings, but be careful not to write things like x cubed or something. Multiplication is a binary operation, and that's the only thing we know. We don't know whether x times x is the same as x times x times x in a given structure. So be certain that when you write these terms, you are very explicit with the order of operations. Don't make any assumptions on how the operations behave. And then you can do the obvious thing. If you then actually have an actual structure A, so think of a ring, for example, and you have a term which has variables x1 up to xn, and then you have elements in your ring, then you can plug these elements into the term and evaluate this polynomial, you would say, in these three elements. But this again works completely generally for other things than rings or objects which you know. Go ahead.
So in the first example,
yes,
you did assume that the plus and the times have a order, right?
Did I?
Otherwise, you have to add another bracket.
Yeah, I should have brackets around the. Thank you. That was a test totally intended. Yes, thank you, Alanda. You're completely correct. Yeah, so I should put brackets around the multiplication sign. Yeah, exactly. Thank you. And then the obvious observation that homomorphisms are also compatible with evaluation of terms, just following from the fact that the operations do this. Okay. And then there's the part which I want to wipe a little bit under the rug, which is what are L sentences. So what you can do with these terms, which we now build, and with the relation symbols which you have, is you can make formal statements in first order language. So you do that, I'm just going to read what the slide says, by meaningfully combining the terms with relation symbols and logical symbols like the for all quantifier, the exists quantifier, or, and, not, and then the equality sign and brackets. So I'm just going to immediately give some examples and hope that the idea is clear from that. So in the language, in the signature of rings, for example, you could write something like, for all x, for all y, x plus y is equal to y plus x. That's an example of a sentence in that signature. Or for all x, x is equal to 0, or there exists a y such that x times y is equal to 1. And two more examples, which I won't read. So, and a set of sentences is called a theory. It's just a definition. And now you could imagine that if you have a structure in a certain signature, think of the signature of rings, and you have such a sentence, then you could say, okay, this sentence holds in this structure, or it doesn't hold. So you could imagine that this first sentence should hold precisely when this addition is a commutative operation. I hope that makes some sense, and because I'm not going to make it super formally precise. I'll give some more examples though. So this is just a thing which I'm writing up there. So a sentence can hold in a certain structure, called a sentence phi. And then we usually write it like this in model theory. So A models phi. Yeah, if it holds, yeah, I'm not defining it. And if you have a set of sentences, you can also define that it holds in the structure if all of the sentences hold. And just to do a little title drop, we also reverse the order in the sentence, and we say that A is a model of sigma if all the sentences in sigma hold in A. Okay, and now we can finally wrap up halfway through the presentation this framework which I promised, that you can capture the notions of rings and groups and ordered groups and vector spaces and so on in this framework of structures and models. Namely, let's define, for example, an ordered group. So what do? We fix first the signature. So we fix the kind of data we have to give to our structures. So in case of ordered groups, that was, what was it again? 2 binary operations plus and minus, a constant 0, and some binary relation less than or equal to. But we don't want just any structure in the signature. We want a structure which is a model of all the axioms which we impose on these functional relations. So I didn't write them all, but whenever you would define what an ordered group is, you would say it's a set with some operations satisfying certain properties, and all these properties can be phrased in this first order language. So yeah, going over them, commutativity of the addition is the first thing. The fact that subtraction undoes addition is the second thing. Associativity of the operation is the third thing. 0 is a neutral element is the fourth thing. Totality of the order, I think, yes. And the last thing here is then is a way of saying, so let me just rephrase it in words. So this is saying for any elements x and y, such that x is less than or equal to y, we have that x plus z is less than or equal to y plus z for any element z. That's the thing at the very last line. Okay, and this now wraps up this framework which I wanted to show of signature, structure, and then putting conditions on the structure. Then we call it a model. So it's a structure with certain conditions. A model of a theory, and the theory is just a set of axioms which we wanted to satisfy. Is that somewhat convincing so far? Then we can get to the fun part. Okay. So what do we do in mathematics? We like to classify things and compare things. Usually in algebra, we compare things up to isomorphism. And you can do the same thing here, right? I defined isomorphism is an invertible homomorphism with inverse, which is also a homomorphism. You can call two structures isomorphic if there is an isomorphism between them. But the things which I suggested before, which I introduced before, suggest a different way of comparing or calling equivalent to structures. Namely, if we have, so always within one specific signature. I don't keep repeating this, so we fix a signature and we work in it. So in a signature, two structures can be called elementarily equivalent if any first order sentence which is true in one of them is also true in the other, and vice versa. So anything which you can say in this first order language, if it's true for the one, it's also true for the other. And then you observe that, okay, I didn't define formulas properly, so you cannot completely prove this from what I said, but it's a very convincing observation, I hope, that if two things are isomorphic, then they are elementarily equivalent. In fact, I think you've probably used this in your bachelor in mathematics, probably that if you wanted to show that two rings or groups were not isomorphic, if you didn't use some cardinality argument, then probably you showed that there was some property which holds in one of the groups but not in the other or something. And then you've shown that they are not elementarily equivalent and hence not isomorphic. So this first arrow I claim is so intuitive that you've used it in your sleep. And on the other hand, if two structures are, this is not super easy to see, but if two structures are elementarily equivalent and finite, or even if a priori just one of them is finite, then they are isomorphic. So for finite structures, say finite rings, finite groups, these two things coincide. But it's easy to see that in general, of course, elementarily equivalence will be much weaker than isomorphism. And in fact, you can give many concrete examples, which I will do just now. So just to name a few. So we work in the signature of partially ordered sets. Then, and considering Q and R as partially ordered sets, I mean, as structures in the signature, they are elementarily equivalent. They are certainly not isomorphic by cardinality arguments, and you also don't think of them as being very similar posets, but somehow they are elementarily equivalent. And the underlying fact is that if one takes any poset which is any totally ordered set, which is dense, which means between any 2 points you can find another point, and which has no maximum and no minimum, then it's equivalent to Q, and thus to R and to all the other ones. So yeah, let me give 2 more examples. So we work with groups, so let's call this the language of groups or something. So 2 binary operations, plus and minus, 0 as a constant element. then here's an example where the sets have the same cardinality but are still not isomorphic. Q and Q to the n for any n, say bigger than 1, as groups are not isomorphic, but they are elementarily equivalent. And in fact, the underlying fact which one can show is that any non-trivial divisible torsion-free abelian group is going to be equivalent to Q and thus to Q to the n for any n. So also, I could also have added R here and R to the n. Yeah. And the final example, perhaps the most. Go ahead.
Does that mean that up to elementary equivalence, there's only a single non-trivial divisible torsion-free abelian group?
Yes, up to elementary equivalence, there's a single non-trivial divisible torsion-free abelian group in this language over here, language of groups, I guess. Sorry, let me check if there are questions in the chat. No, probably not. And then the final, maybe slightly deepest fact of the 4 of them, any 2 algebraically closed fields of the same characteristic are also elementarily equivalent. So having characteristic P is something which you can write down as a first order sentence. It's just saying, so having characteristic 3 is saying 1 + 1 + 1 is equal to 0. So this you can write down in the first order sentence. So certainly if they have different characteristics, they cannot be elementarily equivalent. But if they have the same characteristic, then apparently, and they are algebraically closed, then they must be elementarily equivalent. So this notion of elementary equivalence, you can see by these examples that it's quite a weak notion. It doesn't see the distinction between things which it should clearly see the distinction between. And on the other hand, many theorems which you want to prove about structures are phrased in terms of, or can be phrased in terms of a first order theory, a set of first order sentences, so are preserved under elementary equivalence, which yields the weird situation that sometimes you might want to show some theorem for a certain structure, and it might be easier to show it for a structure which is elementarily equivalent to it, and then show that the theorem is preserved under elementary equivalence. And so I promised I wasn't going to define what model theory is, but if I was going to define what model theory is, then I would say it's the magic which happens in the tension between isomorphism, elementary, and elementary equivalence. But I'm not defining what model theory is, so I'm not saying this. Good. So now let me go through maybe the main part and give examples of 2 big theorems from model theory which can be used to play with this tension. The first one being the Löwenheim-Skolem theorem. Okay, a tiny technical point. Just I want to talk about the cardinality of a signature, and it's simply the largest of the cardinalities of all the INs and the JNs in the case. Almost in the sense that if all of the sets are finite, I'm still going to say that the cardinality is countable. So another, maybe a more motivated way of defining the cardinality of a signature is saying it's the cardinality of the set of, oh, I wanted to say L sentences. I didn't talk about formulas. So the set of sentences, which is always going to be infinite and never going to be greater than, okay, it's going to be equal to this sum above. So just the sum of all the cardinalities of the sets from before. So from all the examples we've seen, I guess the signature of the R vector spaces will be the only one which doesn't have countable cardinality, because always in all the other examples I just had a finite number of symbols. So what does the Löwenheim-Skolem theorem say? Okay, it says a bit more than this, but I'm only going to use this part. It says that if you have a signature and you have some cardinal, which is at least the cardinality of your signature, and if you have any infinite structure, then you can find some other structure B. So this first one is A, another structure B, which is equivalent, elementarily equivalent to your structure, but which has the cardinality which you started with. So loosely speaking, Löwenheim-Skolem says that elementary equivalence can never distinguish between any infinite cardinalities. The actual theorem says a bit more, so it says a bit more about how you can choose this A and B to relate, but I don't want to go into that now. But it says, for example, that if you have a countable signature for any structure you can find some countable structure which is equivalent to it. For any infinite structure you can find a countable one which is equivalent to it. So let's use this to prove one of the four things which I said on the slide before. So you can use it to show all of them. So I will only do one of them. So let's use this thing, this Löwenheim-Skolem theorem, to prove that any two algebraically closed fields of the same characteristic are equivalent, are elementarily equivalent. So there's a small algebraic part first. The algebraic part is that, in fact, if you have algebraically closed fields of the same characteristic and of the same uncountable cardinality, then they are isomorphic. Okay, let me give a quick an argument for this. I don't want to put too much stress on it. It's not the point I want to make in this talk, but just to sketch why this holds. So if you have say characteristic 0, so you have two extensions of Q of the same uncountable cardinality, then their transcendence degree must actually be this cardinality, so they have the same transcendence degree over Q. So they have, there's a bijection between their transcendence bases, which you can extend to an isomorphism between the purely transcendental parts of the extension. And then the remaining algebraic parts are isomorphic by the uniqueness of the algebraic closure, so by the universal property of the algebraic closure. Okay, I'm being very quick with this, but just the underlying fact is algebraically closed extensions of the same transcendence degree are isomorphic. And this follows from the universal property of the algebraic closure. So no terribly deep stuff. But then we are actually done. Do you see? Because if I now take any two algebraically closed fields of the same characteristic, K and L, by the Löwenheim-Skolem theorem, I can find some K prime equivalent to K, some L prime equivalent to L, such that K prime and L prime both have the same uncountable cardinality, say L of 1. But then they are isomorphic by the first part. In particular, they are equivalent. And then we get this chain of equivalences, and we get that K and L are equivalent. So that's the argument. Yeah, good. And so the other ones on the previous slides can be shown. So the second and third point can be shown by just also using Löwenheim-Skolem and a similar argument that in a certain cardinality, all models will be isomorphic. That's the point. Okay, that's one of the two big theorems. And then the other one is called the compactness theorem, also sometimes called the finiteness theorem. And it's about the following. So if you have a signature, if you have some sigma, some theory, you can wonder, does this sigma have a model at all? Can I find at all some structure which satisfies all these possibly infinitely many sentences at the same time? There need not exist in general, right? You might have sentences which contradict each other, like one saying that 1 + 1 is 0, and one saying that 1 + 1 is not 0 or something. But the compactness theorem says that it's sufficient to check that every finite subset of this infinite theory has a model, and then you can already conclude that sigma itself must have a model. And this yields some pretty surprising, or maybe not surprising, results. So here's an example of a you can hardly call it a result, but a principle maybe which follows from the compactness theorem. So again, focusing on the signature of rings. I'm sorry, it's my favorite. If you would have some theorem which can be expressed as a first-order sentence, which holds in all fields of characteristic 0, then it must hold not just in fields of characteristic 0, but in fields of sufficiently large characteristic. So there must be some lower bound m such that in all fields of characteristic at least m, this sentence holds. Okay, let's go. I didn't write it down, so let's try to do it orally, how it follows from the compactness theorem. So suppose not. Suppose you have fields of arbitrarily large characteristic where phi doesn't hold. It means that the theory of if you look at the theory of fields of characteristic 0, where phi doesn't hold, every finite subset of that must have a model, because every finite subset has only finitely many characteristic conditions, so it's going to have a model. And then by the compactness theorem, it will have a model itself. So there will be some field of characteristic 0 where phi doesn't hold. But we assume that phi holds in every field of characteristic 0. OK, I feel like this might be something to write down, which is bad for the people who are following online, I guess.
If you do it on the left.
Yeah, sorry, this was not good to improvise, I guess. People online, I think you can switch between camera and slides. So I'm saying let's take for sigma the theory of fields of characteristic 0. And then I look at sigma union minus phi. Sorry, not phi. And if this thing has a model, then it means we have found a field of characteristic 0 where phi doesn't hold. And I say to show that this thing has a model, every finite subset needs to have a model. But what is this theory of fields of characteristic 0? OK, so it's all the axioms of fields, and you have to add 1 plus 1 is not equal to 0. Sorry, not 1 plus 1 is equal to 0. Not 1 plus 1 plus 1 is equal to 0. So you have infinitely many of these characteristic conditions. But if you have only a finite subset of sigma, then you have only finitely many of these conditions. So if we can find fields of arbitrarily large characteristics satisfying not phi, then we can find models of any finite subset of this theory, which means we can find a model of this theory by the compactness theorem, which says which means we can find a field K where phi doesn't hold, contradicting our assumption. OK.
Exactly, there are some questions from online audience.
Good. Yeah, thanks for the engagement. Indeed, somehow talking about properties of subsets of structures is not so simple in first order language. So characterizing something like simplicity is not so natural in first order language. That was the question, I think. You're welcome. Good. Yeah, so I guess many times when you show a theorem about fields of characteristic 0, which is of this nature, then if you would really want to dig into all the details of the proof step by step and do the bookkeeping of where do we use characteristic 0, when do we divide by a natural number, do we really need to assume that all natural numbers are non-zero, or do we only have to divide by finitely many? Probably all the theorems which this result apply to, if you go through the proofs, then you can see that actually you don't need to assume characteristic 0. You only need to assume that the characteristic is not too small. But the amazing thing about this compactness theorem, I think, is that you don't even have to know what the proof is of phi. Just the fact that phi is a first order sentence means that it behaves in this way, means that if it holds for characteristic 0, it holds for sufficiently high characteristic, which I find quite nice. Small technical point for the people who care. Both the Löwenheim-Skolem theorem and the compactness theorem use the axiom of choice. In case anyone was wondering this, they're not so strong that they're equivalent to it. So it's not like you can derive the axiom of choice from the compactness theorem. It's not that strong, but without the axiom of choice, you won't get there. Good. Yeah, this brings us to the final part. As I promised, a theorem which doesn't talk about models or structures or anything like that, just things which you already knew. The Ax-Grothendieck theorem, proven independently by James Ax and Alexander Grothendieck in the 60s by very similar techniques, which I will show. It says the following: if you take any affine variety, so an algebraic subset of C to the n, so some subset defined by polynomial equalities, and you take some map from this set V to itself, which is injective and rational, by which I mean that just the components are rational functions in the input vector components, then it's surjective. So some kind of pigeonhole principle, you want that injective maps are surjective, but it's certainly not for all fields, it's specifically for C, or algebraically closed fields. Okay, that's the claim. Let's look at the proof. So the proof works like this, or the proof I will give is, rather than immediately focusing on C, let's phrase this property for an abstract field K. So for an abstract field K, consider the property that every algebraic subset of K to the n, V, and for every injective rational map F from V to V, this map must be surjective. And let's wonder whether we can find examples of fields where this property does hold. Okay, think of fields which might satisfy this property. Well, finite fields, of course, because if K is finite, then K to the n is finite, and the subset is finite, and then it's just a pigeonhole principle. You don't even use that it's a rational map. Just injective maps are surjective. Now, if it holds for finite fields, it holds for algebraic extensions of finite fields. This is just a limit argument. So if you have an algebraic extension of a finite field and you have some algebraic set V, then it's defined by some polynomials, and all of these polynomials are actually defined over some finite subfields of the fields. And similarly, sorry, it says polynomial map, it should be rational map. Any rational map has coefficients which lie in some finite subfields, and every element of V is defined over some finite subfield. So you can talk this entire statement back to being defined over some finite subfields, and then reduce to the case from before. So by a straight limit argument, you see that this property passes on to direct limits. So it goes through from finite fields to algebraic extensions of finite fields. In particular, by applying it to the algebraic closure, we see that there exists algebraically closed fields of each positive characteristic P, which satisfy this property, namely by applying it to the algebraic closure of a finite field with P elements. So nothing new happens. I just gathered the conclusions on a new slide. So we have this property, and we know that there exist fields of characteristic P for each prime number P, algebraically closed fields satisfying this property. And then we observe that this property 1, I should have copied the 1 over there, is described by some theory. So this may not be immediately obvious, because, of course, with these first order sentences, you cannot quantify over all zero sets and quantify over all rational maps and so on. But you can pull these things completely apart into a first order theory over K. So you can describe a rational map by polynomials, and polynomials are described by tuples of elements over K, and the same holds for algebraic sets. So you can pull these statements completely apart into being first order sentences completely over K. It's not important that you have a good understanding of how these sentences look like, just that you are convinced that they exist. So what I'm claiming is that there exists some theory sigma, so some infinite set of first order sentences, such that a field satisfies this property, if and only if it's a model of this theory sigma. And then we can wave our magic wand, because then, by the compactness theorem, this principle which I explained here, if there exist algebraically closed fields of each positive characteristic satisfying these properties, then there exist algebraically closed fields of characteristic 0 satisfying these properties, because it's a first order theory. So we can find some algebraically closed field K satisfying this property up there. And then we are done, because algebraically closed fields of the same characteristic are elementarily equivalent. So in particular, K is equivalent to C. So C satisfies this property. Yeah, that's more or less the story I wanted to tell today. I could say more about the ingredients which go into these model-theoretic theorems, but I will leave it up to the audience whether they want to inquire to that. So let me say just what these references are, which I put there. So I put a reference to a blog post from Terry Tao, who talks about this theorem, and also giving different proofs. So it's not just that you can only use these model-theoretic proofs for the theorem, but giving a purely algebraic proof does require delving into all the ingredients, algebraic closures, Nullstellensatz, and so on, and pulling them apart, making sure that there are degree bounds in every step, making sure that you only use finitely many coefficients, and so on and so on. So it really requires digging up all these proofs, which the model-theoretic proof which I gave doesn't require at all. Then he talks a bit more in general about this principle of proving things for infinite fields by using information about finite fields. It's quite nice. And then if you are now convinced and want to learn model theory, I can recommend the book books from Hodges. So he has a book called Model Theory. Then he has another book called Shorter Model Theory, which is the same but shorter. And he really approaches this subject from a perspective of, okay, what is it about? What can you do with it without any of the pedantry of mathematical logic, and really applying it to things you already know, like groups and rings and fields, and with a great British sense of humor, which I can heartily recommend. Okay, that's what I want to say. Thank you.